Video is going to walk you through the process of fitting data to a linearizable model. So I'm going to take you through it for exponential, and then I'll show you what I did for power, logarithmic, and hyperbolic on the other sheets of the Excel spreadsheet. So remember, for an exponential model, what we ended up getting, because y was equal to ae to the rx, we took the log of both sides. So we got log of y was equal to log of a plus rx. And so that meant that there was a linear relationship between x and log of y in the case where we were exponential. And so what we're going to do here is we're going to actually create a new column, which is log of y. Now, just be careful when you do this. So log in Excel by default is the common log base 10. We want the natural log base e. And so when I do log of y, which is b2 here, I'm also going to have to put base. So I want the base to be e. The easiest way to get that in Excel is to use the exp function and take exp to 1. So that's going to give you e to the 1, which is equal to e. A little bit cumbersome, but it gets the job done. So that takes the log base e of b2. We can fill that down. And so the expectation is that if this data is exponential, then a linear curve should fit x comma log of y. And so what we're going to do is we're going to do a regression analysis. So data analysis regression. We're going to select the y range, which is going to be log of y. We want to fit our exponential curve. We want to fit our linear curve to x comma log of y. So we select the x values, we select the y values. So x comma log of y. We're going to put the output range in B23, so that's already right. We've got labels here. So again, make sure you select labels so that it knows. Output range, pick a cell somewhere on the sheet so that it prints it out. And then what we get is that it's showing us that log y is equal to 5.05 plus 0.08x. Okay? Now, of course, we need to translate that back into getting a prediction for y, right? So it's predicting that log, that the predicted value of log y is going to be equal to 5.05, so C39 plus C40 times x, right? So log y is equal to mx plus b. So that's the predicted value for log y, which you can see is pretty close to the actual values for log y that we have. But of course, we actually want the predicted value for y hat, right? And so y hat, if you think back to how we constructed that, y hat is going to be equal to e to the b times e to the mx. Right, that's the formula that we got when we converted our log y equals mx plus b back into an exponential function. Okay, so y hat is going to be exp of the b value, which is C39, times exp of m, which is C40, times our x value a2. Okay, and so that's actually the predicted value of y that we got. If we go in and graph our x and y values, our y hat values, we're going to see that that's a pretty good fit. Okay, and so you can see some randomness apart. we've got a pretty good exponential fit of the data. Okay? Now I just want to caution you, you'll see here that the r-squared value is 0.974 when we did our regression. That's actually the r-squared value for the linear curve fit to x comma log y. Okay? So it's not necessarily the r-squared value for the exponential curve, which is different. So if you wanted to do the r-squared value for the exponential curve, you would take this predicted value, you would take your original value y, you would do the y bar value, do y minus y bar, y hat minus y bar, all of that, and do the sum of squares regression, residual, and total like we did in the previous lecture, and actually could compute that. Okay, but for now we're just focusing on the fitting since we've already talked about that. So make sure you don't use this r-squared value as the r-squared value for the exponential curve. Okay, so let's take a look at the other cases. So for a power function, this was where you had something like y equals a times x to the b, x raised to a power. So in the case of a power function, remember the linear curve fit log x log y. So we took log x log y, found a linear curve between them, right? So log y equals m times log x plus b. And when we converted that back, that became e to the b times x to the m, which is what we use to get our y hat value. And you can see here that we get a predicted model. Our data is pretty chaotic here, but the predicted model fits through it. This looks like it's almost linear. It's not quite. It is very close to linear because you can see the m coefficient is 0.898. If that were 1, it would be exactly linear, right? Because you'd have x to the 1. And so this isn't quite linear, but it's pretty close. Okay. Logarithmic, remember there we fit to y equals m times log x plus b. So we fit to log x and fit y. That's going to give us m times log x plus b. And you can see we get a very nice logarithmic fit to our curve. And then finally our hyperbolic case. Here we're fitting to 1 over x comma 1 over y. Right? That's the data set we want to fit to. So we plug that into our regression. We get our coefficients. You'll see these come out exactly correctly. I didn't actually add any random variation here. And see, you can see it fits exactly to the hyperbolic model that we had. Okay? So that's fitting linearizable models. The main thing is to remember that when you get that y equals mx plus b, that doesn't actually fit x and y. It fits x comma log y, or log x comma log y, or y comma or log x comma y, or 1 over x comma 1 over y, and then you have to transform back to get an actual model that fits your original data and to get your predicted values.